So VLIW took a bit later than expected. Let's see if we can finish systolic arrays today. But now you know the concept and you know its impact. I actually believe that VLIW is a concept that needs to be re-examined, especially within the context of these new machine learning models. I believe with the use of sophisticated machine learning models, you can extract more parallelism through the compilers. But that's something that needs to be seen, of course. So some of these concepts need to be re-examined over decades, in my opinion. That's why these are so fundamental. This is another concept that I'm actually really proud of having been teaching for before they were really popular. I mean, when I started teaching, I said I have to talk about systolic arrays. They're fundamental. They're extremely important. And there's no processor that implements it. Nothing at the time. Today, a lot of machine learning accelerators implement this. Why? Because it makes sense. It fits the model. It has a principled execution model that fits the execution of machine learning workloads. That's why I really, that's the beauty of computer architecture, in my opinion. And that's why we really need to study these concepts, regardless of whether or not they're out there implemented. In a sense, as a purist, I don't really care whether they're implemented today, right? The question is really, does it make sense and what kind of trade-offs they provide? And that may actually enable someone to really implement it downstream. Okay, but before I go into systolic arrays, I will advertise our bachelor seminar in computer architecture. If you're really excited about these topics and if you enjoy these, this is a rigorous seminar on fundamental and cutting edge topics in computer architecture where people, I know you have to take seminar courses, where people present papers critically, review them, and we discuss them. And as I mentioned in this course also, we focus on critical thinking and brainstorming. This is not an easy seminar course. So if you want to actually take a seminar course and just pass it, this is not the course, because this will make you do a little bit more work. And you can learn about that from people who've taken it before. But I think if you enjoy these concepts, this is something that you may want to consider. And you can see some of the papers covered. I don't have time to look at them, but some of the neural network papers that actually we're going to mention today were covered in the seminar in the past. Okay, I've also mentioned that if you're interested in doing research, and I'm a big proponent of bachelor students doing research. I was that bachelor student in my university, University of Michigan, doing research. Please email me with your interest. Don't be shy. This is how you get into research, really. You can see, of course, some important TAs, let's say. I would also suggest taking the seminar course and the computer architecture course that comes after this, and do readings and assignments on your own and talk with us. Basically, it all boils down to this three words: talk with us or email us, basically. That's the way things get started. That's how I got started in research, basically. And there are many exciting projects and research positions, and this is not just me, I should say. You can email any professor, in my mind. I mean, of course, some professors work closely with bachelor students, but everybody needs to do a bachelor's thesis in the end. In my group, we focus a lot on novel computing systems, as you can see, everything about computing systems, new execution paradigms like in-memory computing, hardware security, safety, reliability, predictability, everything that I mentioned in the first lecture. So I'm not going to repeat these in detail right now, but maybe in a later lecture we can discuss more openly. But there's a lot of interesting things here, basically. And if you go to the thesis website that we have, it's unfortunately not very well updated. It's very hard to keep this updated. You can look at the topics over here and figure out what excites you, and then contact us. And you can learn more about us on these. This is my publications page at the end that actually has a lot of information also. And you see a lot of people actually teaching this course. Okay, I've shown you these slides. You can also learn more about our research online. This is a short lecture that talks about our research. And at some point, some of you may decide actually you want to do a PhD or postdoc, and we actually have a lot of PhDs and postdocs, and also bachelor's and master's students that we're proud of, but PhDs and postdocs that fit this list. And they won a lot of awards during their PhDs or postdocs, as you can see. Okay, you can join us, but the key is contacting us. You can also apply here, but since you're at ETH, this is for mostly outside people at ETH. At ETH, since you're here, you kind of have a direct or easy access or privilege to join more easily without going through a more heavy application process, if you will. Taking this course actually is a big part of the application process, if you will. Okay, so if you have questions about this, please email us. I don't want to take questions right now, maybe in a later lecture, because systolic arrays are quite important. Okay, so let's talk about systolic arrays. What are these? Well, basically, if you want to know what are these, I say these required reading, but as I said, there's no reading required, but this is a very nice reading by H.T. Kung, who is one of the inventors of systolic arrays. There's a recommended reading from Google, I will mention. And next week, we're going to talk about GPUs. So you may want to start looking at that. But systolic arrays, basically, I've shown you this slide before. We've been talking about general purpose systems for a long time, CPUs. And we've actually looked at the internals of at least a CPU over here a lot. Actually, this is not just a CPU, but this is a heterogeneous system on a chip. You can see that there's a GPU, there's a neural network accelerator, there's a video processor, etc., that they don't talk about. But on the other hand, there's a special purpose system on the opposite end, and systolic arrays actually fall to the opposite end. So we're going to look at this opposite end today. Tomorrow and next week, we're going to look at this end. And FPGAs you've been looking at for a while. In the future, we may look at this if we have time. But basically, general purpose systems can execute any program. They're easy to program and use. Unfortunately, they don't provide the best performance and efficiency on any application. You can always come up with a special purpose system for a given application. These are extremely efficient and high performance for the application domains that they're suitable for. Unfortunately, they're not easy to program or use. And by definition, they cater to a limited set of programs. Not all programs can be executed on these. FPGAs and GPUs are somewhere in between. FPGAs are quite flexible, but programming them is extremely hard. GPUs are more general purpose over time, but still not as general purpose as CPUs. Okay, so let's start with the systolic arrays. Systolic arrays are actually an execution model. It's not just an accelerator, it's really an execution model. And we've seen multiple execution models. Von Neumann model, data flow model, and then more recently VLIW, which is a variant of von Neumann model. Systolic arrays implement systolic computation, which is going to be more clear when we actually look at what it looks like. Matrix computation is actually some systolic computation. You basically feed the data into a set of functional units, and data flows through those functional units, and you get the output. You can think of it that way. And this is different from von Neumann, different from data flow, although it has characteristics that are somewhat similar to data flow, but not exactly like the data flow that we have seen. Okay, so initially they're designed as special purpose accelerators to accelerate specific applications. What are these? Convolutions, filtering, pattern matching, special purpose matrix vector computations in image and vision processing, signal processing, pattern recognition. This was the reason why people designed these things. These were specialized computations on important applications. And they're currently heavily used in another important application, machine learning, which happens to be the important application of the day. It goes to specialized machine learning accelerators. That said, not all machine learning accelerators are systolic arrays, and not all systolic arrays are machine learning accelerators. Right? There happens to be some Venn diagram where these two sets intersect, of course, but an important set intersection. And their general execution model can be generalized, actually. Their bigger execution model can be generalized and is generalized, as we will see later in this lecture. But they're not as general purpose as the von Neumann architecture. Okay, so motivation. Why were these designed? Basically, folks who designed systolic arrays wanted to design an accelerator that has three properties. One is simple, regular design. You want to keep unique parts, number of unique parts, small and regular. High concurrency, high performance. That's what you want from an accelerator, and high efficiency, hopefully. But at the time these were designed, power and energy were not that important. We're talking about 1970s, 1980s. Power and energy became much bigger concerns in late 1990s, 2000s, and clearly today it's one of the most important concerns. And also, we want balanced computation and I/O or memory bandwidth. Basically, whenever you bring some data, you need to actually process. You need to have some balance between the processing and the bringing data. Data bringing should not be a bottleneck. So they were actually looking forward about the memory bottleneck, if you will. So basically, the idea is very simple. Replace a single processing element with a regular array of processing elements and carefully orchestrate the flow of data between the processing elements. And this is really the idea of systolic computation, if you will, such that they collectively transform a piece of input data before outputting it to memory. We'll see examples of this. So if this is too high level, you'll see an example from convolution soon. And the huge benefit is this maximizes the computation done on a single piece of data. You bring a piece of data from memory, and then you feed it into array of processing elements that the first processing element does something, gives it to the other one. The other processing element does something, gives it to the other one. The other processing element does something, gives it to the other one. So you really have this array. This could be a matrix also. This could be a two-dimensional thing, maybe a three-dimensional thing, actually. Okay, so the big benefit is this. So let's take a look at this. So pictorially, from this paper that I recommended earlier, you have memory and a processing element. And you basically bring one element and then write the data back to memory. You can think of this as the von Neumann processing elements, but we're going to be much more specialized, of course. Whereas here, you bring the data to a processing element, and then that does some computation on it, gives it to the next processing element, which does some other computation on it, gives the resulting data to the next processing element, which does some other computation, and you keep doing this until you finish whatever computation you want and write the data back to memory. This could be taking an element. Each processing element may basically take a piece of the image, for example, and you may be taking an element that you're going to multiply or filter the image with. So, for example, if you're looking for, I don't know, the blue parts of an image, each processing element may be doing some computation on different pieces of the image, or maybe looking for different things in the image, right? Okay, you may actually pass what you're looking for as the element from memory. You may also pass the parts of the image from memory. So it really depends on what you're doing. But basically, this is the basic idea. You bring one piece of data and you operate on it in each processing element, and processing elements communicate with each other, their outputs, and then eventually write back to memory. Okay, so why is this called systolic? Because people thought that this looked like our, let's say, system of how blood flows. You have memory, and that looks like the heart, and data is blood, let's say, and processing elements are cells. Essentially, memory pulses the data through the processing elements. Now, this is important. It pulses the data. There's no instruction that says, I want the data, right? The processing element doesn't demand the data. Memory pulses the data. It sends the data, okay? So we're not going to have instructions initially to ask for the data. Basically, you keep pulsing the data. If all you're doing is, let's say, you have a pattern that you're trying to detect on different parts of an image, you pass the pattern across many, many different parts of an image that's, let's say, distributed across these processing elements, and then you do something basically on those. I'm going to give you a better example, which is really the convolution example, but convolution you may not know. How many people know about convolutions here? Okay, not a lot of people. How many people do not know? Okay, when you take a machine learning course, you have to learn about it, of course. Okay, but why systolic architecture? Essentially, the idea is data flows from the computer memory in a rhythmic fashion, passing through many processing elements before it returns to memory. Similar to the blood flow, you have heart pumps blood to many cells, and eventually let's say, transformed blood goes back to the heart to be cleaned up. Of course, at some point, analogy breaks down, right? Different cells process the blood, and many veins operate simultaneously. And this can be many dimensional, just like systolic arrays. It doesn't need to be a single dimensional. It could be many dimensional. Okay, it's a beautiful paradigm, in my opinion. So why is this good? Because special purpose architectures need what we have discussed earlier: simple and regular design, high concurrency, and balanced computation and I/O bandwidth. So the basic principle is to replace a single processing element with a regular array of processing elements and carefully orchestrate the flow of data between the processing elements to balance computation and memory bandwidth. We're going to see this carefully orchestrate the flow of data. You'll also see it in your homework. You need to input the data at the right times. You need to input the data at regular intervals to make sure that the computation that's done on the PE matches the data, right? If you're doing matrix multiplication, for example, you need to have a way of actually inputting the rows and columns of a matrix at the appropriate times in point, appropriate clock cycles, if you will. And if you do this, you don't need to have any instructions. You basically send the data to this matrix or vector, and after some time, you look at the output. That's it. Now, this is a very different model as what we have seen so far, because there are no instructions, if you will, over here. I mean, at high level, you can build instructions so that you can integrate in software, but one instruction can actually initiate matrix multiply, for example. Okay, so differences from pipelining. You may think, oh, okay, this looks like pipelining. And yes, at a high level, it's pipelining, but it's a different type of pipelining, if you will. The pipelining we have seen pipelined parts of the instruction process. These are complete processing elements. As we will see, they can be very specialized for a function. They're not really executing part of an instruction, basically. So that's major difference. The other difference is array structure may be nonlinear and multidimensional, as we see, depending on the computation that you specialize things for. Programming element connections can be multidirectional and different speed. So we will see some example processing elements that are connected in different ways, let's say. In pipelining, you don't do that, right? Because pipelining is very specialized for instruction processing, and you break the instruction processing into different stages. And also, in the generalization of this model of systolic array, each processing element can have local memory and can execute kernels rather than what is done in pipelining, which is piece of the instruction. So let me give you an example of systolic computation. This is convolution. Convolution is mathematically defined, as we will see in the bottom part of the slide. But this is heavily used in many operations like filtering of images, or filtering in general, pattern matching, correlational analysis, polynomial evaluation, etc. A lot of image processing tasks, and currently machine learning. At earlier times, image processing was the reason why systolic arrays were developed, but now machine learning happens to have convolutions also. So in modern machine learning actually has up to hundreds of convolution layers in convolutional neural networks. So this is the convolution operation, basically given a sequence of weights and this input sequence, you compute the result sequence as defined by this equation. It's basically, you multiply the weights by the input in a particular way, okay? Again, it's not that important exactly how it's done. It's going to be defined if you get exposed to it, but this is very useful. So let me give you more motivation in terms of how it's used in machine learning today. So this is a particular convolutional neural network, which was very popular in the earlier times, let's say. It is used initially for handwritten digit recognition. It was developed by Jan LeCun and his students, and you can actually find videos of him showing this, let's say. Basically, you have this input image. It could be some size. And then you use convolutions and apply some filtering, essentially using convolutions to go to the next step. So a neural network is a multi-layer network. In each layer, you apply some operations to the input. In this case, the input is the image. You try to recognize the image, right? In this case, we're trying to recognize that there's an A. So you subsample the image. You look at different parts of the image and perform some convolution to this mathematical operation to detect what's going on. You can think of it as a sophisticated pattern recognition system, right? That's what's happening essentially. So you can think of this image. In this particular image, it's a 1024 times 8-bit input. If you really want to figure out what's going on in each piece, you need to have a truth table of 2 to the 8K entries, which is a lot. Instead, you have a multi-layer network to try to piece together what might be going on. And even if you have this truth table, that doesn't mean that you have the full picture in the end, right? Because you need to still map the output of the truth table to something. But basically, yes, this is the Lenet network. You do a lot of convolutions. That's my takeaway over here. My goal is not to teach you how this network works. You're going to learn that in a machine learning course. But a multi-layer network, if you think about the perceptron that we've seen, it's a single layer network. It does some operations in a single layer, and then it gives you a binary output, right? Here, the output is, I believe, 10 bits. I don't remember. Don't quote me for it. Something, because I don't remember that number over here. But basically, you do some operations, and then you try to make sense out of pieces of the image, and then you do some subsampling, more convolution, more subsampling, more convolution, some other operations to really try to piece together what's going on. And eventually, the output is a classification of that this is an A, maybe with some confidence interval. Okay, so this is another maybe more easier to look at example. So this is your image. You can think of it that way. This is the input feature map. Or you could think of this as one layer and the output layer within a network. And essentially, this is a two-dimensional image, 5 by 5, as you can see. And kernel is what you use to convolve this with, 3 by 3. And essentially, you apply this gray kernel, that's gray, to all elements of the image or pieces of this input. And then you form an output. And there's a mathematical function that you're applying, this 3 by 3 filter, to every single location over here. And the output is something. And then you do something to that output. Basically, you keep doing this eventually to get the classification. Hopefully that gives you an idea. And this is really more, let's say, fancy way of doing this, as you can see. So you're applying by some, I think in this case, you're taking the dot product, but don't quote me on it also. or you're taking the matrix product, you're multiplying two matrices, as you can see. Okay, if you want to learn more about this, there's a lot over here, but I'm not going to spend more time. You can learn more about neural networks. But essentially, what you're doing is matrix multiplication, if you will, or vector multiplication, depending on how you actually pose the problem. So this is, you basically divide your image into input features, or divide a layer in the neural network into input features. It could be these three different input features. And then you have some convolution filters that you've designed to try to figure out what this is. And that's the inference pass. Basically, you're trying to figure out, you basically trained your network such that you decided these weights of the convolutional filters, right? These are the weights that you apply at a given point in your network. And those are trained to recognize some particular images, for example. So that's how you come up with these. There's a training process that's done separately. Assuming the training process gave you these convolution filters, this is your input. You apply the convolution filters to pieces of your inputs, and then you get an output feature. And then in the next layer, you apply another convolutional filter potentially. But you can basically express these as matrix vector multiplications or convolutions. This is convolution filters over here. This is the input features looked in a different way. You can see that these are these input, and these are these convolution filters. And what we're doing is multiplying this vector with the input features. Okay, so basically this is matrix vector multiplication. Convolution can be implemented as matrix vector multiplication. It could be implemented using systolic arrays as well, as we will see. That's why people are doing this on GPUs as well as systolic arrays today. GPUs, hold on, we'll see. But I will also mention the importance of people doing research. What's enabled this neural networks to actually take off has been some courses that have been taught. Like in 2010, some architecture courses were taught at the University of Toronto that talked about these massively parallel processors. And if you know the name Jeff Hinton, he's a Turing Award winner for neural networks, essentially. He developed a lot of the early neural networks in the 1980s. And some of his students took this course and they basically said, oh, there are these GPUs that we can use to train these neural networks much more efficiently and to do inference on these networks. And they basically were able to do that after this course, and they won the competition. ImageNet competition is an image recognition competition. This is 2012 we're talking about, and this is what the paper they wrote at the end. And they won the competition with significantly higher accuracy than state of the art. You can read the paper. And there are many other papers that are written to make the convolutional neural networks better. Basically, earlier networks had 8 layers, and then they moved to 22 layers over here, as you can see, and they were more accurate. And this actually moves to even more layers. So basically, this was their paper. It was not at the level of human accuracy. Their error rate is still 16% in terms of image recognition. And later works surpassed human level accuracy. As you can see, human level accuracy is supposed to be 5.1%. That's not my number. That's somebody else's number. Okay, it depends on the human probably also. But basically, you can see that first convolutional neural network is here, and modern neural networks are many layers. Of course, there are other types of machine learning as well. So this is one of the motivations of why people are designing specialized accelerators. There's a lot of computation, specialized computation. Let's design specialized accelerators for this. And you can read more about neural networks. You can see that there are a lot of convolution layers, but there are also other layers also. So other layers are also accelerated in specialized accelerators today, some of them. Okay, now let's take a look at convolution, because I'm going to use this to describe systolic arrays. Today, it's also used in machine learning, but in the past, it was used for other tasks. It's still used for other tasks. And this is the equation. And this is a simple systolic array that actually calculates that equation. Now, let's take a look at what this does. Now, it's a linear array of processing elements. And it's actually described over here. This is one particular design. You can see that W's, weights, stay in each processing element. Each processing element is exactly the same. This processing element, this processing element, this processing element. W's are the weights that they store. These weights don't move. They're programmed over there somehow. That's the programming effort. And you feed the variables that you want to calculate from the right to the left. And you feed the input variables, input vector, x1, x2, x3, x4, x5, from the left to the right. And this thing calculates Y1, Y2, Y3 while you feed Y1, Y2, Y3 from the left to the right. This sounds like magic, right? But it's not magic. It's very simple because each building block looks like this. It's a very specialized computation engine. And it's specified over here. Basically, every cycle it does this. Y out equals to Y in, which is the input here, times W times X in. So you basically take Y in, multiply X in with the W, which is stored over here, and Y out gets that value. Okay? So it's a specialized multiply and add, right? It's not an instruction. It's just, this is what the hardware does. And you design the multiplier and adder and put them together. You just need to feed the inputs nicely such that the data flow enables you to get the outputs right. And also at the same time, X out is equal to X in. So every cycle, X out just transfers, basically X in gets transferred to X out. Every clock cycle, okay? Now, if you know that this is what operates, you will hopefully convince yourself that you can connect them this way and supply the inputs and outputs appropriately so that you get the right values that are specified by here. Now, you can do this yourself. I'm going to do this very quickly. But basically, because of the design of this, you need to supply the inputs and the outputs every other cycle. That's how it's designed, unfortunately. You can actually fix that problem. And if you read the paper, it's fixing that problem. Basically, your output, you generate one output every other cycle, if you will. So in the first cycle, you supply things such that X1 reaches here at the time Y1 reaches here. So Y1 reaches processing element 1, let's call it that way, at the time X1 reaches it. In this cycle, there's nothing here, and there's nothing here. So this processing element is doing nothing useful, if you will. So there needs to be some control logic to make sure that that's not doing anything. X2 is in the same cycle supplied to this processing unit. Okay, except it's not doing anything because Y has not reached over here yet. Okay, so basically every other cycle you're supplying X's, every other cycle you're supplying Y's. Let's take a look at what happens in this cycle. In this cycle, what's happening to this input, to this output? And we know that, right? Y out equals Y1 plus W1 times X1. So this will get W1 plus X1. So you will calculate this part of this equation, okay? And then X1 goes here, but it's not connected anywhere, so X1 kind of dies over here, right? And that's good if you look at these equations because X1 is not used anywhere else, okay? That's this particular convolution. Okay, so let's take a look at what happened at the end of the cycle. Y1 is here, X2 is here, right? Yeah, X2 moved over here. Okay, good. Because this processing element didn't do anything in the prior cycle while this processing element was doing something over here. So at the end of the cycle, Y1 is here, X2 is here, and what is Y1? It's W1, X1. Now this processing element will take, set Y1 to previous Y1, which is W1, X1, set this output to W1, X1, which came from here, times W2 times this input, X2, okay? And then pass it over here. Right. And by the time this gets over here in the next cycle, X3 will reach here. And in the next cycle, you will add W3 times X3 over here. Does that make sense? So this is basically calculating that. And you can basically do the same thing while this is happening. Y2 is actually also coming. And you can also look at those calculations yourself. So actually, just to tell you what's happening, while Y1 is here, okay, when Y2 comes here, X2 will come here, okay? And this output will be W1 times X2, right? And similarly, when Y3 comes here, X3 will be here, and this output will be W1 times X3. So by supplying the data in a nice, clean fashion, this simple array of processing elements is calculating convolutions for you. No need for expensive CPUs, expensive GPUs, or whatever. You just supply the data nicely, right? That's the beauty of a specialized architecture. This is what it does. If you ask it to do something else, it will say, sorry, I cannot do that. Well, it won't even say that. You'll need to figure that out. Okay, so there's a lot of optimization you can do to do things, but I'm not going to talk about these in detail. But now you've seen the concept, basically. This is systolic computation. And you keep feeding Y1. And Y1 is actually, the inputs are used many, many times, as you can see. You don't do a load. So if you look at a general purpose CPU, you need to load Y1, X1, well, X1s many times, W1s many times, and do the calculation with instructions and write the result back. This eliminates all of that. A specialized array structure does all of that for you. Okay, so you can optimize. So the key is one needs to carefully orchestrate when these data elements are input to the arrays and when the output is buffered. So this is really the key. Well, of course, you need to design the elements, but once you design the elements, it's really about data orchestration. And this gets more involved, especially when array dimensionality increases. Programming elements are less predictable in terms of latency, so people don't try to do that. These are very, very predictable elements. We will see in matrix multiplication that's used in Google TPUs, for example. They're a very similar structure to what I'm going to show. Let's take a look at the structure. So this is going to be the structure. Let's take a look at how we can multiply two 3x3 matrices. So, and keep the result, final result in processing element accumulators. So this is my basic processing element. Basically, there's an R. R is the accumulated value where each of these will be stored. Where each of these outputs will be stored. C00. This is the multiplication, right? These are the two matrices that are multiplied. These are the results. R is going to accumulate and eventually store these results. There's another way of doing this. Here, I update inside the accumulator. And every cycle, it calculates this. P gets M. Basically, you pass the left input to the right every cycle. And you pass the top input to the bottom. Q gets N. And the computation is R is equal to R plus M times N. So you're really multiplying two values and accumulating them in R, which is essentially what matrix multiplication is. If you want to do a dot product, that's what you do. Now, if you want to do a 3x3 matrix multiplication, you have 3x3 elements, and the result will be stored in each of these. And this is how you supply every cycle different elements of each matrix. Matrix B's first row goes first. Matrix A's first column. Matrix A's first row goes this way, left to right. Matrix B's first column goes this way. And the first element that's computed is A00 times B00, as you can see, and that's going to be accumulated. In the next cycle, you're going to add A01, B102 here. In the next cycle, you're going to add A02 times B20. And that's exactly what you want. You want to take the dot product of this row with this column. That is C00, right? Now, this is beautiful. While this is happening, of course, in the next cycle, this element will get A00. Because it gets in the next cycle, in the first cycle, you get 0. You send 0 over here, right? To make sure that it doesn't do anything in the first cycle until it receives the first element over here. True over here also. This processing element receives B00 in the next cycle. So in the first cycle, it should not do anything, no harm. Similarly to this element receives B00 and 2 cycles later. So it should not do anything for 2 cycles. That's how you orchestrate the data inputs, essentially. And you can go through the calculations, but in the second cycle, what this will calculate is, actually, let's do a column calculation. In the second cycle, what this will calculate is A10 times B00. Am I correct? Yes, A10 times, okay, something. Yeah, exactly. A10 times B00, right? Which is going to eventually get you a C10. Okay? And you can convince yourself that this works. And in your exam, you may have a question that basically asks you to input some things, or there are variants of these questions that you may see in your homework, for example. Basically, we can ask you what this element does, give you the computation. We can ask you how you feed the thing into the systolic array, given that this element does something. So there are many, many interesting variations in the end. As long as you know how data needs to flow and how a systolic array operates, it's very easy. Okay, so I'll give you more examples. This is essentially what Google has built, basically. They have built a matrix vector unit, or matrix unit, as they say, and we're going to take a look at that. And this is very powerful in their systems. But systolic arrays can actually be two-dimensional, as we discussed, but they can also look like this. They can also look like this. My favorite example is from the earlier paper, one of my favorite examples. So basically, you can chain together these systolic arrays to form powerful specialized systems. For example, this systolic array is capable of producing on-the-fly least squares fit to all the data that has arrived up to any given moment. It's a real-time processing system from 1980s, right? Early 1980s. So what this systolic array does, so you can see the carefully orchestrated data inputs. This systolic array does orthogonal triangularization. That's one way of actually helping with least square estimation. A lot of matrix operations, let's say. Matrix operations are not just matrix vector multiplication. You do a lot of other matrix operations. And then you input the data into this weird looking systolic array, which solves triangular linear systems. And then you need to buffer the data carefully so that the data arrives at the right point to the right processing element. So it's all about orchestrating the data. So, okay, so I've given you the concept. The huge advantages are, this is a very principled design. It efficiently makes use of limited memory bandwidth, balances computation to I/O bandwidth availability. That's one of the biggest benefits of this. You basically chain lots of elements, orchestrate data flow so that you don't need to access memory, hopefully. You can implement systolic arrays on FPGAs also. FPGAs are a substrate to implement things as well, but that's subject for something else. They're very specialized, as you can see. Computation should fit the processing element organization and functions. And specialization buys a lot of things. Efficiency, simple design, high concurrency, and high performance. And it's good to do more with less memory bandwidth requirements. The big downside is the same thing, which is they're specialized. It's not that they're principled. That's not a downside. Being principled is not a downside, but being specialized is a downside, basically, because they're not generally applicable. Some computation needs to fit the processing element functions and organization. And if you want to make them generally applicable, it becomes more complicated. Okay, so more programmability. People have tried to make this more generally applicable. Each processing element in a systolic array can actually store multiple weights. Weights can be selected on the fly using multiplexers. And this eases the implementation of more sophisticated techniques. If you just want to implement convolution in a particular way, okay, you can do it with the technique we talked about earlier. But if you want to do adaptive filtering, adaptive sampling, etc., now you need to actually decide which weight you're going to use, depending on what you're doing. So this enables more programmability, but it comes with more cost. Now, if you take this further, it enables the systolic computation concept. Each processing element can have its own data and instruction memory, actually. Data memory can store partial and temporary results or constants. And this leads to stream processing or pipeline parallels. More generally, stage execution. So I'll give you the idea. So you can have a loop that looks like this. You can have a code in stage A, stage B, stage 3. In each iteration, you have A, B, C. These could be quite specialized computation. I'm not telling you what they are. I mean, one of them may be matrix multiplication, fine. But basically, if you keep doing this many times, instead of executing it like this, you may actually have, you could execute it in a single processing element like this. You may actually have 3 different processing elements specialized for each different type of computation, AI, BI, CI, and then feed the data to that. And this is a simple loop we're talking about. This is a general purpose programming model. So you can actually transform a general purpose programming model to more systolic computation. And this is called stage execution. You can read papers about it. We don't have time to talk about it. But basically, you can divide loop iterations into stages or code segments called stages. This is essentially what I showed you. A, B, C. These could be very special. And these different stages can execute on different cores, and cores can be specialized for the computations that execute on them. Okay? Okay, so I've kind of generalized the model. This is not what people who wrote the systolic arrays envisioned in 1970s, 80s. But today, this is what some things are being done. For example, video processing that Google built that has some systolic components to it. File compression is another example. Again, for example, you can have a file that you're compressing lots of files and you want to build a specialized compression engine for files, whatever, videos, for example. So you may actually divide your processing into stages, and each stage may be very specialized hardware. And then you basically operate on different data that's flowing through these stages. Okay, so I talked about a lot of things. So you need to think about this a little bit more, of course, but this is really the high-level systolic computation example. This is not exactly what was envisioned in the 1980s. But those folks also didn't envision machine learning accelerators, right, clearly. So let's talk about advantages and disadvantages, and I'm going to talk about how this is employed in the field today. So basically, huge advantages, you have your special purpose, you get high efficiency. You make multiple use of each data item. You reduce the need for fetching, refetching, better use of memory bandwidth. high concurrency, and regular design. So it's easier to implement. Disadvantages, it's not good for irregular parallelism. Forget about irregular code on this, essentially. Special purpose, not generally applicable. It needs software programmer support to become more general purpose. And it also needs software programmer support actually to make sure this works. Because you need to feed the data somehow, and there needs to be some system level support to feed the data, right, inside there. It's difficult to program if the problem doesn't fit well. So these were actually implemented at CMU. H.C. Kung, who developed the paradigm, actually implemented these. I'll give you the history a little bit more. They basically use this to accelerate vision and robotics tasks. And they had a linear array of 10 cells at the time. Each cell is very simple, as you can see, about 10 megaflops. And it was attached to a general purpose host machine, just like an accelerator, just like machine learning accelerators are attached today. And they had a high level language and optimizing compiler to program the systolic arrays, which is interesting. And this is what the system looks like, basically. It's a systolic array for image processing or vision processing or robotics, which is a lot of vision processing also. And I'm not going to go into it, but it's essentially a systolic array. But this is a modern systolic array. And this is the paper that basically says we have built a systolic array from Google. And essentially, it does what I showed you earlier, 2D matrix multiplication. And you can see the buffers that buffer rows and columns of the matrix. And there's some additional structures over here to do additional operations. So basically, rows and columns flow in this matrix unit. If we had time, we would actually go through this in more detail. We don't have time. So I'm going to flash some pictures over here. So you can see that Google has improved this. But they're at the core, these are all systolic arrays, if you look at it. And you can see that they actually use it for many, many things over here. Reinforcement learning, recommender systems, natural language processing, computer vision, 1 exaflops per board. It's amazing, I think. And I'll finish with some readings. This is one of the readings that they actually published. They talk about this publicly. This is a reading that's coming up soon. We have actually worked on the edge TPUs, and this I will motivate later when we talk about memory. But tomorrow, I should also say that machine learning acceleration is not just about systolic arrays. Tomorrow, we're going to see SIMD concepts. And these machines that are built for machine learning acceleration use the SIMD concept. This, and these use FPGAs. So basically, all of these paradigms can be used to accelerate different things. And tomorrow, we will see the SIMD paradigm. So have a good evening. I'll see you tomorrow.